Basically, the cavitation bubble concentrates the energy of a plasma of deuterons and electrons that get their final chemical push as the 10,000 K plasma cools to 2,500 K, and the recombination allows for the D plus an electron goes to a deuterium atom plus hot shock wave. A 10 to the 12 meter change in volume in 6 femtoseconds. The period to form one deuteron-electron bond. This is enough time to focus heat that fuses two Ds to alpha, producing one helium atom. The culmination of this confined heat, producing pulse shock wave, in the small space of MC of deuterons is destruction of the target foil lattice containment via Nebel-Ames-Lawande's interactions of charged particles on surfaces, specifically deuterons. There are 3 authors for this paper. One is Tom Claytor, who works in the Los Alamos area. The other is Roger Stringham, that works from his home in the island of Kauai, of the Hawaiian Islands, and Malcolm Fowler, who works also at Los Alamos and is well known for his expertise in mass spectroscopy. Cavitation sonoluminescence. The sonoluminescence starts a chain of events. The chart shows the photon emission. The blue are 50 nanometer sonoluminescent emission photons. The red is a cavitation frequency input at 1.6 megahertz. You can see they are coupled together. A 50 milligram polycarbonate sonoluminescent reactor encloses a cylindrical PZT piezo. Data was collected with the MPPC 400 pixel photon counter donated by Hamamatsu, about a 10 millivolt average signal output. The cavitation bubble cycle resonance frequency was set and tuned. Look for the water spout and maximize. The bubble collapse jet plasma implants hot electrons and deuterons into the target foils. The RF apparatus showing transmission line and piezo antenna at the bottom of the RF reactor. Photo of an RF reactor that should be made of ceramic tube producing the water spout. The MC clusters. Temperature must be higher than 2500 degrees K. Charge separation exists in the 6 femtosecond time frame. This is a static system except for the most massless electron that are compared to motion of lattice atoms and MC deuterons. The probability of recombination in the time frame was high, producing a shock wave and an alpha. Helium measured. The mass spec helium measured by Brian Oliver at Pacific Northwest National Lab, Roger Stringham's paper titled Helium Measurements from Target Foils recounts this measurement. Helium-4 was found in active center, average helium content of 3 pieces, about 40 plus or minus 2 times 10 to the 12th atoms for the activity in the center of 1/3 of the target foil. No helium was found in the edge piece, nor in the two FCC palladium exposed target foils measured. Photo of titanium 3A target foil where helium was trapped and measured. Scanning electron microscope, SEM photos. Photo shows the titanium target foil surface with a 1 micrometer titanium oxide tube exploding from the surface and its shadow on the surface of the foil. Very similar to the above SEM photo of titanium 3A that B. Oliver mass spec measurement of lattice captured helium atoms in the titanium lattice and no helium found in the two palladium target foils. A difference between BCC and FCC lattices. PD target foil example in the FCC palladium lattice where all these lattices produce craters from their ejecta. Palladium, a FCC target foil where helium was found. RF4 input 2 megahertz, about 4 times 10 to the 14th helium atoms measured by Malcolm Fowler's mass spec. Gases collected from the saturated argon gas phase over the cavitating D2O in the RF reactor were measured. Note, the 6-watt 250-second heat pulse fits the helium data. Run RF3 helium-4 found in HOH needs more work. Target foils BCC and FCC. The BCC target foil lattice of 2 atoms retains helium and the FCC lattice of 4 atoms ejects helium. Red shows the MC cluster located in the interstitial space of the target foil lattice surface. The MC contains several deuterons that are cooling in a 6 femtosecond time frame. Within the MC, around 2500 K, an active free electron combines with a deuteron. Where the MC was destroyed, the shock wave was produced, and from the debris, 1 alpha was produced. Using a 1700 megahertz polycarbonate 50-gram cavitation reactor with a circulation of DOD produced high temperatures in the target foil lattices. This is shown in photos of melted target foil debris scattered about after a few minutes of exposure. In the HML laboratory in Los Alamos, the argon saturated DOD cavitated at 20 watts for 10 minutes. It shows unusual debris shown in the next few slides. A pure nickel foil after a 5-minute exposure produced pure nickel spheres and a hole in the target foil surface. The spheres varied from 1 to 15 microns in diameter, and they are spread out on the target foil surface. There is still destructive power in the cavitation bubbles at 1700 kilohertz. A copper target foil was exposed to low frequency, 30 kilohertz, shows cavitation erosion in the active zone at the edge of the foil where it was clamped and where the activity was amplified. Also, internal hotspots at the edges of the foil produced pure and oxidized copper nodules. The mass spectrum data measured by Malcolm Fowler will be described in the paper that follows the video presentation. One can understand at about 2500 degrees K the probability in the time frame of 6 femtoseconds, the time for one electron to capture one MC deuteron, making a bond event. This is a good fit with Lawande's like charge attractive forces that play a part in the compression of the MC deuterons. This explosive increased reaction volume and the MC density during the capture of the deuteron atom initiates a destructive shock wave with its hot debris field forming an alpha. Helium-4 was measured by mass spectrometry on several different occasions.